All right. After going to start a new topic now. We finished thermodynamics, so the new topic is going to be charges, forces, and fevers. Forces between charges. Yeah. So forces, charges, forces, and fields. So, as with any topic in basically science, physics, chemistry, it's a fruit or a consequence or conclusion of of decades, centuries, right, of work. So when we say there are how many types of charge? Pluses and minuses, right? That's a consequence of many centuries of, so we're getting to the conclusion, right? We're getting to the conclusion. We're not going through all the history, how things were discovered, because that would take us, first of all, a long time, and secondly, it's not the aim of the class. The class is how do we use these conclusions to calculate things. So our starting point is going to be from what's called Coulomb's law. That's basically what we're going to start. But I'm going to mention there are two types of charges, the pluses, the minuses. So there is the pluses and there are the minuses. Now free charges, the charges that are found in nature, they're usually multiples of the charge of the electron or the charge of the proton. Okay? So protons are positive, electrons are negative. So the charge of a proton is, so I'm going to state it and I will give you the unit and that will tell us in what units charges are measured. It's a new quantity, it's not mass, it's not any of the quantities that we know so far. It's 1.602 times 10 to the minus 19 of this C here. C is Coulomb. And sometimes this 1.602 is given the symbol E. The charge of proton. Did I? This one? Oh, yeah, it's off. All right. Oh. So E. So this is the elementary charge. E. The charge of an electron is just minus E, just negative that number. Same number, but negative. So the electron and the proton, they both have the same exact charge, but one is plus, one is minus. So that's the first thing. Now it's measured, so charges are measured, charge is measured in a Coulomb. That's the unit. Okay? Now, more experiments, they show that if charges are both positive or both negative, like charges, if they're like, they will repel. And if they're opposite, they will attract. So like charges repel, opposite charges attract. Okay? And then comes the conclusion, or the question, we want to be quantitative. What's the attraction? How strong is that force? And how does it depend on the charge? And maybe how far should the charges be, and so on. Okay? So that's the conclusion we will get to. So let's say I have a charge here, charge Q1. By the way, like position, we usually use X for position. Charge is usually little q or capital Q for charge. I know we use capital Q for heat, but now we're in charges, so it's also capital Q or little q. So Q is like this. To kind of not confuse it with the number 9, I always draw like a little tail this way. So here's another charge, Q2 here. And let's say they're separated by a distance r. They're separated by a distance r. And the question is, what's the force between them? with what force does charge 1 exert on charge 2, and what force does charge 2 exert on charge 1. As you may think, what do you think? Let's say charge 1 exerts 10 newtons of force on charge 2. How much force would charge 2 exert on charge 1? 10 by Newton's third law, right? You should kind of guess that. Yeah, so we'll see the form of the force is symmetric. So the force between the two charges, and this is just the absolute value, okay? The magnitude. We'll get to the vector form in a moment. Is some constant k, we'll talk about that constant in a second, and then q1 times q2 divided by the distance between the two charges squared. Okay? Two charges squared. That's the force. Force, of course, is in newtons. Okay? Force is in newtons. Charge 1 is in coulombs, charge 2 is in coulombs, and the distance is in meters. So distance squared is meters squared. So what is this k? Well, yeah.
So that would be the force of Q1, Q2,
And the reverse, yeah, that's the magnitude, yeah. And you see, if you switch the q's, it's the same, right? It's the product. If I put q1 times q2 or q2 times q1, it's the same force.
What value?
It depends. If it, no, it's the charge, right? It could be an electron, it could be a proton, it could be multiples of that. And we'll do some examples of numbers. Yeah. So K, well, first of all, this law here, this is Coulomb's law without the vectors. We'll write the full Coulomb's law with vectors, but this is called Coulomb's law. So Coulomb has the charge, the unit named after Coulomb, and then the law named after Coulomb, and this one is Coulomb's constant. Coulomb's constant. How much is it? Well, it's experimental value is, I will give you the approximation. It's, if you want the exact, just go through the notes. The exact is like 8.9875, it goes on. But we'll just write it as 9 times 10 to the 9. The units would be, the left side is newtons, so this one has to have newtons. We need to cancel the meters squared at the bottom and Coulomb squared at the top. So that's Coulomb's constant. Okay. So this is Coulomb's law, and we use it to find the force between two charges. Again, I would put vectors. Vectors will come back in an example or two, few minutes. Another way you would see this law written as, sometimes you would see it this way. There is Q1, there is the Q2, there is the R squared, but the K is written different. It's written like this, 1 over 4 pi epsilon naught. Yeah.
Wouldn't the M squared and the C squared be like, flip? Because it's R squared is in meters, so
Is
it's on
epsilon
the
what?
bottom.
Yeah, R squared is meters squared, but on the bottom, when I multiply it by meters squared on top, it cancels, right? Yeah. That way, when everything's multiplied, I end up with
something goes pakai Q-nya Q besar.
So this epsilon naught here, this thing here, is the same. You can use K is equal to 1 over 4 pi epsilon naught. So you can solve for epsilon naught, right? You can, it would be 1 over 4 pi K. So epsilon naught, how much is it? It's approximately 8.85 times 10 to the minus 12. And it would be, has the reverse. So Coulomb squared, newtons times meters squared.
What is it called?
Huh?
What is it called?
Epsilon.
Epsilon.
Epsilon 0 or epsilon naught. Yeah.
So it is my normal Coulomb
I think it's called permeability of permittivity of free space. Yeah, permittivity of free space, and then there's another one called the permeability. I keep getting them confused. This one is the permittivity of free space. So we just call it epsilon naught. It has a value, it's a constant. So let's go to our first example to get a feeling of this law, how to use it, and the strength of these electric forces, right? Strength of electric forces. So we all know, or we should remember this law.
Let's say the epsilon 2 1
This
over
is a mass, and this is another mass,
It's not one, so it's not.
and they're separated by a distance r. What's the gravitational force, Fg? Between them? G, M1, M2 over R squared. Excellent. Good. Remember what G was? 11 newtons meters squared per kilogram squared, right? That was G, the universal gravitational constant. Okay, so the question is, which force is stronger, the electric or the gravitational? Of course, we gotta know what the charge is and what the mass is to figure which one is stronger. But let's just take two typical charges and two typical masses. Take a proton and an electron. We want to compare the electric attraction between the proton and the electron and the proton versus their gravitational attraction. So I want to do this. I want to compare the electric force. This is Fe, the electric force, to Fg, which is the gravitational force. To compare them, I'll just take the ratio of the two equations and see, is one 10 times more, maybe 100 times, maybe 300 times, maybe more, maybe less. So we want to do this. The electric force divided by the gravitational force. The electric force, right? We'll just take an electron and a proton. Okay? I'm going to take an electron and a proton. Electric force is K, right? And then what? Q1, Q2 divided by the distance between them squared, right? And then the mass, and then this one, the gravitational is going to be G. First mass, second mass divided by the distance squared. So notice the distance squared cancels. So all I have is this. K, charge 1, charge 2 over G, mass 1, and mass 2. Let's plug in some numbers. Again, what are we comparing? Electric to gravitational. And we're doing it for what case? An electron and a proton. Okay. So we're going to plug in the charge of an electron, the charge of a proton, and the mass of an electron and the mass of the proton, right? Electron and a proton, they happen to have the same charge, absolute value, the same magnitude of charge. And I'm looking here for the magnitude of force, so I'm going to plug in the numbers. K is 9 times 10 to the 9. Q1 is 1.6 times 10 to the minus 19. And charge 2 is 1.6 times 10 to the minus 19. Electron and proton. Again, here is a question. Why didn't I plug in the minus sign for one of them? We're just looking for magnitudes. Yeah, we're just comparing which force is stronger and by what factor. And we're not worried about the minus sign. Now G is 6.67 times 10 to the minus 11. And then M1. Proton's mass is about 1.6 or 1.7, right? Times 10 to the minus what power?
Minus 27.
27. Electron. Lighter or heavier? Lighter, much lighter. Actually, something times 10 to the minus 31. kilograms.
How was it? What
So,
was it? Ito
uh,
masama.
Again, we're doing it for the case of an electron and a proton. So I plugged in the charge of an electron and a proton, minus sign, ignore it, because we're just magnitudes, and these are their masses. And now we want to find approximately what the force is. I don't care about all the decimals and the numbers in front, so we're just going to work with powers of 10 just to make it quick. So powers of 10, look at this.
1.67.
I got a 1.6 on top and this 1.67. I'm going to just approximately cancel that. The 9 here and the 9 here, they approximately cancel, right? I'm not looking for, again, for a precise answer. I just want an order of magnitude. And let's see what I have. This 1.6 divided by this is approximately going to be another number that's like 3 or 4. So I don't really care about 3s and 4s or 6s and 7s. So just going to cancel all that stuff. So let's look at the powers of 10. 10 to the minus 11, or 10 to the 11, 10 to the 27, 10 to the 31. Add them all together. What do you get? Let's see. 69, 11, yeah, 10 to the minus 69 on the bottom. Goes upstairs, it becomes 10 to the 69. Okay. Now, 69 minus 19 is 50. 69 minus 19 is 50, right?
Wait, how is it?
And then these two, they add up to minus 10. So 50 minus 10 is 40. So we'll just be satisfied with 10 to the 4. So, or 10 to the 39, maybe 10 to the 41, something, somewhere around there. The bottom line is this: the electric force is much stronger than the gravitational force. Yeah, just a little bit. So, it's not 2 times, it's not even an Avogadro's number of times. It's even bigger than that. Okay, so the question I asked my other class was, if the electric force is this much stronger, remember when you talked in mechanics, the planetary motion, the moon orbiting Earth, you cared about their masses, right? That's the force that contributed to the gravity. But if the electric force is this much stronger, why didn't we use that to calculate the motion, right? Because it's much stronger. In fact, it should dominate so much, the gravitational force should not even show up, pretty much, right? Because it's so much bigger. Do you know it? Yeah.
I don't think Earth has its own charge. Like, isn't Earth, it all equals out to like about 0 for the entire thing?
That's the answer. So atoms, they have protons and electrons. So overall, when you add them together, everything is essentially neutral. So it adds up. The total charge on Earth is approximately 0. When you add all the pluses and minuses. And the same thing for, let's say, the moon. Okay? So yeah, so that's why the electric force, even though it's so big, if the Earth was positively charged and just positive charges, and then the moon was also just positive charges or negative charges, then you wouldn't care about gravity at all. It would just be plus charge, the electric force. But it happens that they're neutral, so it is the gravity that takes over. Okay, now the vectors. Come back. So let's talk about, because forces are vectors, and we care about in what direction and so on. So here is Q1, and here is Q2, right? Charge 1, here is charge 2, and here is a vector R1, 2. R1, 2 is a vector that points from charge 1 to charge 2. Okay? R1 is a vector, R1, 2 is a vector that points from from Q1 to Q2, and R12 hat is a unit vector. R12 hat is like this. R12 hat is a unit vector that points in the same direction as R12, but it has magnitude 1. So it's the vector R12 divided by its own magnitude, right? That's how you find unit vectors. So for example, if I have a vector A, and I want to find a unit vector that points in the same direction as A, I will take that vector A and divide it by its own magnitude, then I get myself a unit vector. Clear? Again, charge 1 is here, charge 2 is here, and R12 is a vector that points from 1 to 2, and it has a magnitude of the distance between the two charges. Distance between the two charges is R12. Okay? So, let's write Coulomb's law with vectors. The force that charge 1 exerts on charge 2. Let me write it in words first. Force exerted by 1 on 2 is this. The force from 1 to 2. The force due to charge 1 on charge 2 is equal to. The magnitude is given by what I wrote earlier. That's the size. That's how big it should be. So it's K, charge 1, charge 2, divided by the distance from charge 1 to charge 2 squared. So that's just that. And now I need to get the direction right. Okay. So let's get the direction right, and I will show you it works in all in all 3 or 4 cases. To get the direction right, I need to include the unit vector from 1 to 2. Unit vector from 1 to 2. Does red show up fine, or it's not? It's good. So let's double check that this makes sense. This equation makes sense. Let's say both charges are positive. Right? If both charges are positive, is the force going to be attractive or repulsive? Repulsive. Meaning, the force that charge 1 applies on charge 2 is going to be in what direction?
Or charge 2.
Like this, right? So charge 1 pushes charge 2 away if both are positive. Let's say. If both are positive, K is positive, both charges are positive, the distance squared is also positive, so everything is positive. So this is just a positive number times this unit vector that points that way. So a number times a vector that points that way would just be another vector that still points that way. Right? As long as the number is positive. Okay, let's do it for the case where both charges are negative. Minus times minus is plus. So this constant would still be positive, and the force would still point that way, meaning repulsive. So if both charges are negative charges, like charges repel, so it will still be repelled. So this formula would still do the job for us, right? How about if 1 is plus, 1 is minus? They have opposite charges. Plus times minus is minus. So overall, this number would be minus. Now take a vector that points this way and multiply it by a minus sign. You get the vector that points that way. Meaning the force now, the force that this one exerts on this would be attractive. So charge 2 would feel a force toward charge 1. So it would be attractive. Okay? So that is that. Now another way you would see this, force is the following way. It's K, Q1, Q2 divided by R12 but cubed, and then R12 hat. Not R12, I'm sorry. R12 the vector. Okay. I think, how did the square become a cube? Well, I substituted for the unit vector, this R12 hat. R12 hat is the vector divided by its own magnitude. That's the vector, and then its own magnitude on the bottom multiplies this and becomes cube. So it comes like this. So Coulomb's law, it drops as 1 over r squared. The farther away the two charges, the less force there is. Right? The less force they will be. Yeah. Yes, there are where it's more convenient. Yeah. So for example, if both of them are along the x-axis, I would want to use this. If it's off-axis, then this one is more convenient. In fact, we're going to do an example, and we would see exactly that. How am I? Yeah. It's about 10 minutes. And then I just have to mention the superposition principle. What if I have several charges? Let's say I have charge 1, 2, 3, 4, 5, and I want to know how much force they exert on charge 6. How do I do that?
Just subtract it.
Just add them, right? Find the charge, the force that 1 exerts on 6, plus the force that 2 exerts on 6, and 3 and 4 and 5 did the last one. And then you just add them together as you add them. That's what the superposition principle says. Basically, the force that charge 1 applies on 2, or on 6, is not affected by the presence of another charge. So meaning, like, the net force would just be the sum. Force 1 plus 2. Seems obvious, but we just still have to state. Okay. Here is an example. Here's X, here's Y, here's a minus charge,
Starts with
here's a plus charge. Let's say this one is positive Q, this one is minus Q. This is a square, it's supposed to be a square. And then here is a 1/2. So let's name them 1, 2, 3. 1, 2, 3. And the distance this way is A. And let's say A is, I think, 2 centimeters or so. Okay. Yeah, 2 centimeters, or 0.03 meters. And the charges, going to right here, Q is equal to 6 times 10 to the minus 6 coulombs. So I have that's the charge. So charge 1 is 6 times 10 to the minus 6. Charge 2 is minus 6 times 10 to the minus 6. And charge 3 is, charge 3 would be what? 3 times 10 to the minus 6. And the question is this. Find the net force on, find the net force on 3. Right, the net force on 3 would be the force that 1 exerts on 3 plus the force that 2 exerts on 3. Right? Two forces. There are 2 forces on the charge. And so, yeah.
Is it a square?
It's a square.
Okay.
Yeah, it's supposed to be a square, yeah. Yeah, so it's A on each there. Good. So the diagonal would be what? How far? To A? Yeah. So let's first find F13, F23, and we might have to come back to this example, or maybe I will leave it as an exercise for you. So let's start with F13, will be K, Q1, Q3 divided by R13. So for this one, since you asked earlier, should we use this or this, right? This form or this form. For this one, it's more convenient to use this, form. I will tell you why it's more convenient in a second. Here is why. Here is the vector. Here is the vector that points from charge 1 to charge 3. Here is R13. Who can tell me how to write R13?
0.04
In symbols. Use the symbols A and maybe
IJ.
yeah. So R13 points this way. So if you follow R13, it will take you A units to the right and A units up. So it's actually what? A what? I hat plus A J hat. Yeah. So it's easy to write this one. To find the unit vector, you have to divide by its own magnitude, which would involve square root. But here is the R13. The magnitude is going to be A squared plus A squared square root, which is the square root of 2A. And R13, if you cube it, what do you get? What's the cube of square root of 2? It would be square root of 8, right? Which is 2 root 2 A cubed. So let's substitute here. So we get K, and then Q1 is Q, right? Just Q. I will substitute the numbers at the very end. Q3 is also, no, it's half Q. Q3 is half of Q. And then R13 cube is 2 root 2 times A, and then the vector is A I hat plus A J hat. So you get the 2 comes down, so you get K Q squared over 4 root 2. We can factor the A's here and make this a 2. You get A squared, and then I hat plus J hat.
How is
Sounds good? So that's F13. We can simply substitute the numbers now to get a vector with both the magnitude and direction. I will leave it in symbols for now. So that's F13. We dealt with this part. Let's do the F23. For F23, it's going to be K, Q2, Q3, divided by the vector that points from 2 to 3. For this one, which form we will use? I will come back to it in a second.
R squared above.
The unit vector, because in this case, what's the unit vector? From 2 to 3. It's just I hat, yeah. Right? The vector that points from 2 to 3 is I hat. So we don't have to, so it's easy in this case. Yeah?
On the first part, why did we use the R cubed?
This
Yes,
one.
yes.
So we can either use this or this,
Yeah.
right? It's up to us.
Okay.
So it's more convenient in this case to use the R cube. Why? Because if I ask you, R13 is the vector that points from 1 to 3. That's an easy vector to write. It's A units to the right and A units up. So it's easy to write that. But if I say, what's the unit vector that points this way? I don't think it's, at least it's not obvious if you're not experienced with it. just write it down. What is a unit vector that points this way? It's a combination of I hat and j hat. That unit vector, yeah, it's not easy to write, at least not immediately. So it was more convenient to use this for that case. Okay. Whenever the unit vector doesn't point in the x direction or the y direction or the z direction only, it's more convenient to use this. If the unit vector just is in the x direction or the y or the z, then it's more convenient to use this one. And then, so in this case, for example, it's clear, let's see why it's more convenient to use jet. It's just this, R2, 3, hat. Now, what's a unit vector that points from 2 to 3? From 2 to 3 is strictly to the right. What's a unit vector that points to the right?
I.
I had it. So in this case, it's simpler to just, this was easy. That's I had. I don't have to work too hard for that. Now for here, now how far is 2 from 3? A, so A squared on the bottom. And then K is K, and charge 2 is minus Q, right? It's negative. And this one is half of Q. And so we get minus, and then K, Q squared over 2A squared, and then I half, right? That's the force between 2 and 3. And then to find the total force, I need to add this to what I have here. And then you're asked to find the magnitude and the direction. So how many people still remember how to do vectors, like magnitude, direction, all that stuff? Okay, good. Right? If you don't, you would have to. Because the electromagnetism, basically, vectors are there all the time. So, and we will deal with my time is up.